Okay, so what we're going to talk right now, we will look at the examples of relationship between Ka and Kb for conjugate acid and base pairs, right? For conjugate acid and base pairs. So we already know that to calculate the relationship between Ka and Kb, we will use the following expression, Kw equals Ka times Kb, or pKw equals pKa plus pKb. Okay, so then let's look at this example. Calculate the values of Kb of conjugate bases of two acids. So we have hydrofluoric acid. And just to bring you nice memories from the lecture, we all remember that in collegiality we all decided that hydrofluoric acid is the correct weak acid. Okay, so then we can talk in terms of values of K that are less than 1. And we have additional weak acid, that is the phosphoric acid. And phosphoric acid, it has 3 ionizable protons, so it's polyprotic acid. And if it's a polyprotic acid, so the donation of the first proton will be described by Ka1, second proton by Ka2, and third proton by Ka3. So then we are asking to calculate the values of the pKb of the conjugate bases of these two acids. So the conjugate base of hydrofluoric acid will be fluoride. And we need to calculate the value of Kb of the fluoride. The conjugate base of the donation of the first proton of the phosphoric acid will be H2PO4 minus. And we are asked to calculate the value of Kb of this base. So then, if we're talking about these values, right, so we will use the aforementioned expressions of, so we know the values of the Ka. So the value of K of the hydrofluoric acid is, is given right here. So if we know the value of the Ka of the hydrofluoric acid, and we're assuming that we're working at 25 degrees of Celsius, so then at 25 degrees of Celsius, the value of Kw is 1 times 0 times 10 to the negative 14th. So what we know here, we know the value of the Kw, we know the value of the Ka, and we need to calculate the value of the Kb. So we can do it for the hydrofluoric acid. Right, so let's do it for the hydrofluoric acid. So the value of the Kb will be 1.0 times 10 to the negative 14th divided by the value of the Ka of the hydrofluoric acid. And how do I know the value of the Ka? Right, I looked at the table 16.2 and in the appendix D of the textbook. So this is how I found this specific value. And this is the value of the Kb for the fluoride ion, right? So it's fluoride ion. Fluoride ion, we remember this, that fluoride ion actually is a weak base. Okay. So now let's look at the next example. So let's look at the H3PO4, which is the acid, and its conjugate base of this acid. So now to calculate the value of the Kb of this conjugate base, we need to take the value of the Ka of this acid and to do the following calculation. Or basically this substitute to this expression. So now the point is for the phosphoric acid, we have 3 values of the Ka. So what value of the Ka we're going to take? So of course this value of the Ka, which says 1, is the donation of just first of these 3 protons. So this is the value that we're going to take. Okay. So then this is the calculation that I did. So I took the value of the Kw, I took the value of the Ka, I substituted it here, and this is the value of what I got, and this is the value of the Kb. So okay, this is Kb and this is Kb of the H2PO4 minus as the base. Okay, so now let's analyze a little bit the data that we have. So if we compare the value of the Ka of the hydrofluoric acid to the value of the Ka of the phosphoric acid, so we clearly see that phosphoric acid is a stronger acid, right? So let's write it down. So phosphoric acid is stronger than hydrofluoric acid. But now let's compare the relative strengths of the conjugate bases. So when we look at the values of the Kb, so this is the value of the Kb for the conjugate base of the phosphoric acid, and this is the value of the Kb for the conjugate base of the hydrofluoric acid. So we clearly see that the conjugate base of the hydrofluoric acid is stronger. Why? Because negative 11 actually is bigger than negative 12, right? So let's write it down. So the F minus, which is the conjugate base of this acid, is stronger base, right, base, than this base right here. And it clearly brings us to the idea of what we discussed in the beginning of the chapter 16, in the beginning of the acids and bases, where I gave you relative strengths of the acids and bases. So when we have the strong acid, its conjugate base has negligible basicity, and if you have a strong base, its conjugate acid will have negligible acidity, right? And it can be seen from this calculation that we just did from this relationship. Speaking about the weak acids and weak bases, the weaker the acid, the stronger its conjugate base, right? So this is very, very important rule that we defined qualitatively, but now we actually are talking about quantifying this relationship through this expression. And what I want to do an example with you. So let's look at the following question. Right, so this following question talks about different bases. So let's write these bases down. So we have NH3, we have C5H5N, we have H2NOH, we have NH2CH3, and you are given here also different values of the Kb. And the question actually asks us here, using the data in the table, which of the conjugate acids below is the strongest acid, right? So, but we're talking, so it's interesting what the question is asking. So the question is asking us, using the data in the table, which of the conjugate acids below is the strongest acid? But we're given bases, right? So what we have to do, we have to write down actually, so these are bases, right? We have to write down the molecular formulas of the conjugate acids of these bases. So let's do it. It's going to be NH4 plus, C5H6. So here we have 5, here we're going to put 6, N plus, okay? So H2 NOH, so let's actually add here 3, and plus will be on nitrogen always. So if we have here NH2, so let me put NH3 and put plus here and add CH3, right? So the idea here that you will understand in future in organic chemistry, so where to put the hydrogen. So this particular class, it's not really important, but it will be seen in future that the hydrogen has to be added as close as it possible to the nitrogen, right? Not here. It's important. So basically, as close as possible to the nitrogen. So we have conjugate acids, And in this case, right, let's write down the expressions, the values of the KBs, right? So the values of the KBs are 1.8 times 10 to the negative 5th, 1.7 times 10 to the negative 9th, 1.1 times 10 to the negative 8th, 4.4 times 10 to the negative 4th, right? So we will apply this rule that the weaker the base, the stronger its conjugate acid. So for this reason, we do not actually even need to calculate the values of the Ka to compare these acids, right? So the only thing that we need to do, we need to find the weakest base, right? So we need to find the weakest base, and it will give us the strongest conjugate acid. So to find the weakest base, we have to compare these values right here and find the lowest value out of this 4. And the lowest value will be for this specific base, right? So this base has a lowest, let me close it actually, a lowest KB. So hence it is a weakest base, and it will give us strongest conjugate acid, right? So then, speaking about conjugate acids, so this acid out of 1, 2, 3, 4, so third one will be strongest, right? So this is the strongest conjugate acid. So you see, you do not need to do any calculations. You just need to apply this specific reciprocal relationship between the values of Kb and Ka. And you can see that the stronger the weak acid, the weaker its conjugate base, and vice versa. Okay. So now, what I want to do, I want to solve an additional example. So we can see that fluoride ion can actually be a weak base. So we will combine these two concepts. So first of all, I want to show you an example of the problem where we're combining two concepts. So the concept number 1 that will be combined here will be the calculation of pH of a weak base solution. And second concept that we're going to be using here is that actually we can calculate the value of the Kb if we know the value of the Ka. Okay? So calculate a pH of a solution of 0.15 mole concentration of potassium fluoride. If we know that the Ka of the hydrofluoric acid is it's actually 7, right? It's 7, 6.8 times 10 to the, so what was the value of the Ka here? 10 to the negative 4th. Okay, 10 to the negative 4th. Or sometimes in some textbooks you will find 7 times 10 to the negative 4th. Okay, so this is an example. Okay, so first of all, let's think what we have here. So what we have here is the specific solution of potassium fluoride. So potassium fluoride is salt, right? So potassium fluoride is salt. So all salts of potassiums, they are strong electrolytes. So what does it mean? It means that when you take potassium fluoride, let's say solid, and you put it in the water, when you prepare the aqueous solution, it will dissociate into potassium and fluoride ion. Okay, so if this is the case, so potassium, it will be a spectator ion here, for the reason that we will describe in the next video. But what we have here, we have a fluoride ion that actually acts as the base, as the weak base with the water. So what does it mean? It means that, and let me take you to the next page. The fluoride ion in the aqueous solution, it will react with the water and it will act as the base, meaning that it will abstract a proton from the water and we'll get hydrofluoric acid and OH minus. So if fluoride reacts with the water and it abstracts the proton from the water to give us hydrofluoric acid, so look at this, what happens. It actually increases the concentration of OH minus in the solution. So it means that it changes the pH. So for this reason, what we have to do, we have to think of what is the equilibrium concentration of this OH minus in the aqueous solution. So then let's see what we start with. So since we start with 0.15 molar concentration of potassium fluoride and it's strong electrolyte, so it will give us in the aqueous solution actually 0.15 molar concentration of potassium plus and 0.15 molar concentration of the fluoride minus. So in the aqueous solution of the potassium fluoride, we have 0.15 molar concentration of fluoride ions. So then what we have to do, we have to set up the ice table, right? And in this case, what I have 0.15 molar concentration of the fluoride. So let me just put M right here, okay? And let's say at the beginning, I do not have, before all this chemical reaction happens, I don't have any hydrofluoric acid and OH minus. So then, to calculate the pH, right, remember pH is equal to pKw minus pOH. And when I'm talking all this pH and pOH is all concentrations of the H plus and OH minus at equilibrium. And if I know the concentration of pOH, or concentration, of OH minus at equilibrium, right here, right? So this is the OH minus at equilibrium. I can calculate the pH of this solution, right? So I have to set up the ice table again. So water will not be in the picture. And again, I have to actually talk about, so fluoride acts as the base, right? And what I have here, I have to set up the expression for the equilibrium constant, which is OH minus times HF over the concentration of F minus, and all these concentrations at equilibrium. So if I know the value of the Kb, again I will set up the expressions for the equilibrium constants, equilibrium concentrations, and I will solve for X. And I will find X, I will find the equilibrium concentration of OH minus, so everything will be fine. So let's first of all set up the ice table. So the ice table will look like this. Again, I will not do step-by-step solution because we already did ice table many times. So it's X of fluoride will react, X of hydrofluoric will be produced, X of OH minus will be produced, equilibrium expressions of the equilibrium concentrations will be 0.15 minus x, x, and x here, right? So what I have to do, I have the equilibrium concentrations, and I will set up them into this expression for the equilibrium constant, right? But the point is, what is the value of the KB here? So let me take you back to the question itself. And what I'm given here, I'm actually given the value of the K of HF. And I know that the value of the Ka of HF is related to the value of the conjugate base of HF through the following expression. So I have Kw equals Ka of HF times Kb of its conjugate base. So, and I know here the value of the HF. I know that I'm working at 25 degrees of Celsius. I know the value of the Kw, so I can calculate the value of the Kb. So let's do it. So the value of the Kb of F minus will be value of Kw divided by value of the Kb of the HF. And it will be, when I do my calculations, 1.0 times 10 to the negative 14th divided. So let's do it actually using my app. You can use your calculator. Right, so I have 1.0 times 10 to the negative 14th divided by 6.8 times 10 to the negative 4th. Yes. So it's, or even let me try to do it 7.0. Yeah. So 1.4. So the value of the Kb will be 1.4 times 10 to the negative 11th. And I know everything here, so let's do it. So Kb is 1.4 times 10 to the negative 11th equals x squared over 0.15 minus x. Again, what I'm doing here, so look at this, the value of the Kb, the value of the equilibrium constant is 10 to the negative 11th. It's very, very small. It means that the equilibrium lies to the left. It means that this x will be very small, and if this x is very small, right, so then I can make my assumption that I like to make, that x is very small, so then the equilibrium concentration is basically numerically very close to the initial concentration of the fluoride, and I can remove this x from here, so to eliminate solving the quadratic equation. But remember, I have to always check my assumption at the end, meaning that if I make the assumption that x is way, way smaller than initial concentration of the fluoride, so then I have to check it, validate it, right? So when I do my calculations right here for x, so x will be equal to 1.4 times 10 to the negative 6, and x, remember, this is the equilibrium concentration of OH minus. And if I know what is the equilibrium concentration of OH minus, I can calculate the POH. So let's calculate the POH. POH will be negative log of 1.4 times 10 to the negative 6. And it's 5.84. And the pH will be 14 minus 5.84. And pH will be 8.16, right? So we're almost done. But please remember that if I make this assumption, I have to check it, right? So let's check this assumption. Let's calculate the percent of ionization, which will be the concentration of OH minus at equilibrium over the initial concentration of my base times 100%. And when I check the percent of ionization, it will be something like 9.3 times 10 to the negative fourth percent, which is of course less than 5, and I'm all set, right? So my assumption was correct. So now let me zoom out of all this story and let me summarize. So we were asked to calculate pH of the solution of 0.15 molar concentration of fluoride salt. So, and we were given the value of the Ka. So what do we have to do? We have to analyze first. So when you have the salt of potassium, so what happens? All salts of the potassiums are strong electrolytes, and in the aqueous solution it will dissociate into potassium plus and fluoride minus. Potassium plus will not react with the water, right? Will not react with the water for the reason that we'll discuss in the next video, right? So alkali and alkali earth metals, they don't react with water, they are spectator ions. Fluoride, though, it will react with the water because it's a conjugate base of a weak acid, hydrofluoric acid, right? So what will happen here? The fluoride ion in water will act as the base. It will pick up a proton from water and will produce OH minus. If we are changing the concentration of OH minus, if we're producing the concentration of OH minus, so we are changing the pH, in this case of the water, right? And speaking about it, so what will happen, since it's a strong electrolyte, in the aqueous solution from 0.15 molar concentration, we will get 0.15 molar concentration of fluoride minus. So this will be our initial concentration of the base. So then we set up the ice table and we calculate the equilibrium concentration of OH minus. So we made to calculate this, we made an assumption that because of the value of the Kb is that small, so it means the equilibrium lies to the left and not much of the OH minus will be produced, right? The fluoride will not be very reactive. And our assumption was that this AX is actually very small, and it made us to assume that the equilibrium concentration is actually close to the initial concentration. And when we made this assumption, it allowed us to eliminate from solving the quadratic equation. So we solved for X, we found the equilibrium concentration of OH minus, we calculated the pOH, and knowing this, we could calculate the pH. The pH of this solution is 8.16. Of this solution, of this concentration. If we change concentration, we change the pH. Of course, we checked our assumption, and our assumption was perfect, so it was less than 5%, so we don't have to go back and solve quadratic equation. And again, it is very important to pay attention to the fact that we were given the value of the Ka, even of the Ka of hydrofluoric acid, even though we're talking about a completely different compound. So why Ka? Because in reality, the fluoride is reacting, which is the conjugate base of the hydrofluoric acid, and we calculated the value of the equilibrium constant of the reaction of the fluoride with the water, which is called base dissociation constant, using the following expression, which relates the values of the Ka and Kb of the conjugate acid-base pair. So with this, I will stop, and next topic we'll discuss the relative acidity and basicity of salt solutions.